Hello and welcome to the day 5 of 4th week of this lecture series. So, this week we have been talking about different pulsing techniques, and we have talked about Q switching and cavity dumping, and we are going to talk about the third most widely used pulsing technique, that is mode locking. So, we will be talking about mode locking. So, before we start talking about the principle of mode locking, let me tell you that this particular technique of generating pulsed output is used to generate very short pulse. When I say very short, it means approximately 10 power minus 12 to 10 power minus 15 seconds, that is picosecond to femtosecond. So, this generates picosecond to femtosecond pulses. So, this picosecond or femtosecond pulses, this time duration is known as ultra short. Ultra short pulses. And why do we need ultra short pulses? Because there are so many processes that that take place in nature, in chemistry, in biology, which happens really fast, which are known as ultra fast processes. So, this guy, it probes, it is used to probe ultra fast processes, where some chemical reaction or reaction dynamics, etc. So, now with this knowledge, we will start looking at how to mode lock a laser, how to generate this ultra short pulses starting from a continuous wave laser. So, in earlier classes we have learnt about the standing wave condition in a cavity. So, this we have already seen. Okay, so earlier standing wave condition. What is the condition? That not any wavelength can be sustained in a cavity, there has to be a particular relation fulfilled. So, that is given by m lambda equal to 2L, where m is the order of mode, particularly longitudinal mode. So, m refers to order of longitudinal modes, L is the cavity length, right. So, I can express this in terms of frequency also. So, if I write the frequency, I can write mc by 2L. If I be very proper, then I should write, instead of mc, I should write mc prime, where c prime is nothing but the velocity of light divided by the refractive index of the medium. Okay. So, there are so many frequencies that can satisfy this standing wave condition within a cavity, correct. And there will be a separation between two successive frequencies. So, say nu 1, nu 2, nu 3, nu 4, so on up to nu m. So, there will be a gap between nu 1 and nu 2, or nu 2 to nu 3. What is that gap? That also we have learned. So, gap between modes is given by delta nu, and delta nu is equal to C by 2L, correct. Now, what is the approximate number? Okay, that also at one of those classes we have seen that can be in the order of 10 power 8 hertz. Okay. This is just a number, okay, that you can easily figure out by given certain L values. So, this is a huge number. Now, the particular modes that will be within the laser output is determined by, of course, the cavity length and also the spectral bandwidth, that emission bandwidth of the laser active medium, correct. So, if you remember, we have solved one problem using the example of Heine laser. Given a bandwidth and given a length of the cavity, how many modes can be accommodated within that spectral bandwidth. So, if the bandwidth of the spectral bandwidth of the active medium is small, then the number of modes also will be small there, and if the bandwidth is very large, we will have large number of modes. So, in certain lasers, like particularly in solid state lasers, if I be even more particular than solid state tunable lasers. Okay. So, for example, titanium sapphire, or dye laser. We will talk about these different lasers, okay, in the coming week. So, this type of lasers, the emission line width, okay, the emission line width is quite broad. If you are familiar with the fluorescence spectroscopy, and if you have seen fluorescence spectrum of dye, say for example rhodamine, you will know that this is fairly broad. Okay, their full width half maxima is in order of tens of nanometers, which is really broad. So, within that particular broad spectral envelope, the number of modes will be also large, correct. So, number of modes falling under the or within the envelope is very large. Okay. So, we have seen that in case of Heine laser with a 10 centimeter cavity length, number of modes within the spectral bandwidth is only 1. If I increase the cavity length to 30 centimeter, the number of modes are 3. So, compared to these, for a laser system like dye laser, where spectrum is really broad, the emission spectrum is really broad, the number can be as large as 1000 to 10,000 quite easily. Okay. So, if I have so many modes there, what may be my what can be the good thing or bad thing happening there? These modes, each individual modes will have their phases. So, it is not necessary that one mode will be related in terms of phase to another mode. So, what I am saying is that at this condition, normally the the phases of the modes will not be correlated. Okay. So, none of the modes are correlated with each other in terms of phase. What will happen then? So, each of the modes may contain several photons, right. Now, these photons belonging to different modes having different phases, they will ultimately interfere, and the result of this interference is to generate very random amplitudes of signal, and the amplitude also will be very small in the level of fluctuations. So, because of this there will be interference which will lead to random fluctuation of intensity, okay, and this intensity is also extremely low. So, if this is not desirable, correct. So, what one can do is to try to bring some phase relation between different modes. So, now let us have a look at let us look at this situation pictorially. So, let us consider a cavity and a particular mode. So, this green color, this is one particular mode. Okay. So, here in green color it is shown one particular mode. So, let us call this is mode 1 in my this picture. Now, let us have a look at another possible mode. Okay. So, the mode is shown in orange color. So, this is my mode 2, and if we keep going, then this blue one, this is mode 3. Let us have one more, this red color, mode 4. I can have several such modes, like I said, like 10 to the power 3 to 10 to the power 4 number of modes. For simplicity, let us consider 4, which will be good enough to explain our problem. Now, just expand this, let us expand these modes. Right now I have shown it in a superimposed way. Okay. Now, if I separate them, they will look like this. Now, if you just take a pause and have a look at all these different modes here and try to see if there is any phase relation, you will be seeing that there is no real phase relation, that it is not that after a certain number of repetition the modes are constructively interfering. Currently, the kind of modes that we have chosen, they will not do that. So, the result will be a random intensity like a fluctuation due to mostly destructive interference. So, this is what is shown here. Okay. So, this is the result of interference. Fine. So, what mode locking will do? Mode locking will bring in a phase relation between these different modes. So, now look at these guys. So, you see here all of them are in phase. Okay. So, they are all will constructively interfere. Now, you keep going, you come here, you see again same thing is repeated. again here. So, if I am looking at the green one, so after every 3 pulses, 3 waves, they are repeating themselves, the condition of this constructive interference there. So, the resultant is there will be constructive interference at certain point in time window. At a certain time there will be constructive interference, everywhere else there will be destructive interference. So, what is happening? So, I have several modes oscillating with several frequencies. Now, I somehow lock all of them or bring in a condition where all these modes, all these waves, their phases are in unison. So, therefore, because they have different frequencies, so when there will be unison like this, I will have constructive interference. Everywhere else you can see this will interact with this guy or this guy, they will definitely cause destructive interference. So, only here I will get intensity and everywhere else I see nearly 0 intensity. Very good. So, this is already is like creation of a pulse. So, if I look at it in this fashion, so I can see that how this constructive interference is giving rise to a solid intensity. Now, if I can choose my cavity length in a way that I collect only up to this, what will happen? Within the cavity I will have only one pulse, okay. That is that can have round trip. So, if I can have that, then this is what I will get. So, there are several modes here, okay. So, similarly I have taken 5 modes here and they constructively interfere here, everywhere else they are destructively interfere and give 0 intensity. And this is my cavity comprising of high reflector and output coupler. So, if this guy, this particular pulse, it moves back and forth through the active medium, this only gets intensified more and more, okay. And output coupler being partially transmittive, every round trip will throw some light out of the cavity. So, the distance between 2 successive such pulses will be equal to 1 round trip time, right. This is very easy to understand. I have somehow created a phase relation between all the possible modes in the cavity, which particularly fall under the emission spectral bandwidth of the active medium, and then I have chosen the cavity in such a way that the result of this constructive interference, which is given by this peak here, will be the only one pulse within the cavity moving or making round trips, okay. And in that case every round trip will give me one pulse. Whenever it comes and hits this output coupler, I get one pulse. So, the distance between 2 successive pulses is 1 round trip, okay. So, I said like this time period, this time period is the time gap between pulses. T is essentially 1 round trip time. Okay. And one can actually show that this period is equal to 1 upon delta nu. Okay. So, in other words, it will be 2L by C. and also one can show that the resultant pulse width. So, I am talking about this width, this is my pulse width, and we denote it as tau p. And let me be a bit clear. So, if I have pulses like this, so my drawing is little bad here. Okay, so this is my tau p and this distance is my t. Okay. So, this tau p, that is the pulse width, it can be shown that it is somehow related to the del nu and the number of modes in this fashion, where n is the number of modes that are taking part in this interference. Okay. So, from this relation, what can we say about the nature of pulses? Okay. So, let us quickly write down that one. So, t equals to 1 by delta nu and tau p equals to 1 upon n delta nu. So, this is like almost equal to, okay. There is some constant term like a pi. So, from this relation, what we can say is that for say for a number of mode, let us take n equals to say small n, okay. And then I have a picture like this is the intensity, and let us just consider 2 successive pulses, okay. There are pulses beyond, okay. So, this is my time axis. Now, if I double the number of modes, what will happen? So, from this relation we can see this will be essentially multiplied by 2 in the denominator. So, tau p will be now half. So, what I have is nothing is happening to my period, time period, but my pulse width is totally changing, right. So, this is the effect of number of modes. So, for example, if I can increase the number of modes in the cavity, okay, by my own design, by simply adjusting the cavity length, then for more number of modes, my pulses will be shorter and shorter and shorter. So, this is one trick that one can use to make ultra short pulses. First place, you create a phase relation between the number of modes, which will lead to constructive interference at one particular point and everywhere else destructive interference. Select one particular pulse thus created to oscillate in the cavity. This oscillation will intensify only one pulse, and that is quite narrow. Then now, if your number of modes involved in this interference is much more, then this pulse is even shorter. Okay. So, you can create shorter and shorter pulses by increasing the number of modes. So, at this point let us get an idea like how to estimate what what kind of pulse widths that we can expect. So, let us take an example, okay, and let us try to estimate. So, the most common mode locked lasers is titanium sapphire. Okay. So, let us take titanium sapphire laser. Okay. So, titanium sapphire is the active medium. So, what is done here? Okay. So, before that let us give some numbers, the bandwidth of this one. Let us take the number that I have with me, 128 terahertz, and a tentative cavity length around 200 centimeter. Now, what I have to find out for this given bandwidth and the cavity length, what can be the pulse width, what is the shortest pulse width that is possible. So, we will have a limiting value of possible pulse width that is possible. So, how to find that out? So, we should be able to do it because we have done similar type of problem in other context. So, delta nu first is C by 2L, which is divided by 2 into, right. So, I did it in meters. So, this will give you approximately 75 into 10 to the power 6 hertz or 75 megahertz. Now, if the distance between two pulses in frequency unit is 75 megahertz, then what is the number of modes, okay, in the cavity? So, the number of modes is, now I can easily find out. I have this bandwidth. So, within this bandwidth, how many such gaps are possible? That will give me the number of modes, so, right. So, essentially it is given by the bandwidth divided by my gap between modes. Okay. So, this is 128 terahertz divided by the gap between mode is 75 megahertz, right. So, this is equals to 120 into 10 to the power 12 hertz, 75 into 10 to the power 6 hertz. So, this will give you the total number of modes, which I will write the final value, that is 1.7 into 10 to the power 6. So, this many number of modes that are possible within the cavity. Now, what is the time gap between each pulses? Okay. So, I have found out delta nu. So, I can easily figure out what is t. So, time gap pulses, that is t, equals to 1 upon delta nu, that is equals to 1 upon 75 megahertz, and if you calculate this one, the final value will be 13.3 nanosecond. And finally, what is the pulse width? Pulse width tau p is equal to 1 by n delta nu, correct. So, n is this number of mode. So, 1 by 1.7 10 to the power 6, right. So, this is the number of modes, correct. and 1 by delta nu we have just found, that is equals to 13.3 nanosecond. So, 13.3 nanosecond. So, this will give you a value of around 7.8 ish into 10 to the power minus 15 second. So, roughly I can say this is around 8 femtosecond. See this, I have a 200 centimeter long cavity and having a particular bandwidth of 128 terahertz. I calculated how many number of modes are possible, I calculated the gap between those what is the gap between the pulses, and ultimately I found out the pulse width, and the pulse width turns out to be 8 femtosecond. This is really short. Okay. So, in reality, if the number of modes are less than this theoretically possible number of modes. So, if suppose instead of say 1.76, if we have the number of modes equals to say like 5 into 10 to the power 5, of course, this value will increase, right. So, for lesser number of mode, tau p will increase. So, that means this is my limiting value. So, this is my limiting value of tau p. So, I can see that if I can create a phase relationship between the modes of a cavity, I can create pulses, not only create pulses, but we can create really ultra short pulses as I just showed. So, we will stop here today, and in the following class we will look at what are the possible ways, practical ways to bring in this phase relationship within the modes and create mode lock lasers. Thank you very much for your attention.